Hi, this tutorial is going to take a look at our regression Excel calculator. And so what we've got here is the tab for calculating a regression. We also have the F distribution, which will be useful for looking at the statistical significance of the regression. And we'll come down here. This part of the analysis assumes you've already learned about ANOVAs, or the analysis of variance, and that you've also studied correlations. So the top part doesn't assume that, but I'll just let you know that up front. So you might want to review information about ANOVAs before watching this video. But even if you haven't watched that video, you can still learn about the top part. So the problem is, okay, a researcher collected the following set of data on years of education, so that's what X is, and number of children, right, so that's what Y is, for a sample of 10 married adults. Draw a scatter plot of the data, right, so that's what this is over here. The lowest X value is 8, so it doesn't start over here at 0, but starts at 8. And then we're just plotting X and Y on the axis, right? So that's what these dots are doing. And then this regression line is right down the middle of all those dots, right? It minimizes the distance between all of the dots. That's what the regression line does. So how did we make that? That's a scatter plot. So we just simply highlight the two columns of data that we'd like to use for the scatter plot. And then we insert the scatter plot, which is this one. And then, as you'll see once you create it, that you can format the axis and the grid lines. Format the plot area. Okay, all these options, and one of these options, of course, is to draw a regression line. So that's just a descriptive looking regression line. So what we want to do now is discover what the mathematical formula is for this line. Now, it's simple enough so far. It's more complex when we do what we call multiple regression, which has multiple variables, because it doesn't lend itself to this kind of graphical representation. At most, 3 variables can be plotted in that way. So in order to calculate the regression equation, we're going to need to get the squares of our columns of data and then the product, just like we did when we calculate a correlation. Right? And actually it turns out that these are highly related to each other. And so the regression equation requires us to calculate the sum of squares, and these are the equations for the different sum of squares that we'll be looking at. So sum of squares for x, y, and product. So using the sum of the x square column, right? So there's our x square, there's our sum, and the y square column, and its sum, and then also looking at the sample and the averages, right? So the sample is 10. These are the averages for x and y, 13 and 2.2. So all those values are just getting plugged in. And the Excel formula that we're using here is just simply bringing those values into that equation. So in this case, for this sum of squares of x, it's d14 minus b17 times b15 squared. Right? So b15 is that average of x squared, right? b17 is the sample, and d14 is the sum of the x square column. Right? We do that for y also, and then we do that for the product column also. So the product of x and y, sum of the products there. There's our formula. It's drawing in the x and y averages and the sample, right? Just like it says to do right there. Okay, so once we have our sum of squares, we can estimate b and a, So what are those things? B is the slope, right? And so the slope is sum of the product um, divided by the sum of squares x. So this value, minus 43 over 104, that's what this is doing right there. And then the a value is looking at um, the mean for y. So the mean for y is here in the table, right? So there's y. The mean for y is here in column or cell B15, right? So that's what B15 is doing here. C15 for y and B15 for x. X is also in there in the formula. So you can see that's the equation. And A is going to wind up being our y-intercept, which would be if we extended this line out to 0. Where would it land? And what we see from the calculation is it would land on 7.575, which is actually above where we are in terms of the maximum value on the chart. Once we know the slope and the y-intercept, we can use that information to make predictions. And that's what this area right here is set up to estimate predictions of y based on a value of x. So if a couple has 10 years of education, with our y-intercept of 7.5 and our slope of 0.416, we created an equation in this predicted y cell. So it's B50, which is A, right, 7.5, plus C50 times D50, so B times X. So negative 0.4 times 10. So in other words, if a couple has 10 years of education, we predict they will have 3.4 kids. Of course, you can't have a fraction of a kid, so really we just predict 3 kids. Maybe we'd round that down. And if we plug in other values there, let's say they had 12 years, now we predict 2.6 kids. But again, that rounds off to 3. Let's say they had 16 years of education, we're just now predicting 1 kid. So that's kind of the nice thing. Once you have this set up, you can come up with actual predictions of y. If we wanted to, we could actually create another column of the predicted y values based on different levels of education for x. All right, so that's the first part, which is the line. Another question we have is how much of the variation, how much of y are we explaining with x? So this is sort of like a correlation question. So the coefficient of determination will tell us that information. And for that, we actually need, you guessed it, the correlation. So correlation, if you look at the correlation equation, you'll see the numerator is identical to what we have as the sum of products here. Right? And the numerator and the denominator, the sum of squares for x and y, square root of them. Right, so this is the formula for the correlation, but subbing in this notation for the sum of squares and the sum of products. All right, so that's how we got our correlation of negative 0.86. And the coefficient of determination, you see the formula is just the square of that. So the square of the correlation is the coefficient of determination. And so we can interpret that as the explained variation. So we've explained 75% of the variation in children based on years of education, which is very high. So really a predictive variable, high level of predictability there. The coefficient of non-determination is the amount of unexplained variation. Right? So what else is left unexplained after we include that piece of information? And so in a multiple regression model, we will add more variables to try to account for more variation. So that's the second piece here. The third piece is asking the question, is this model statistically significant? In other words, can we generalize from the sample of couples here to a wider population of couples? And that's what the F-test is going to tell us, which is an analysis of variance. So we're actually kind of working backwards, but in order to calculate the F-score, we're going to be looking at the relationship between the mean squares for the regression and the error. And in order to get those, we have to start off looking at the sum of squares for the regression and the error divided by the relevant degrees of freedom. So that's why we're kind of starting up top here. So the sum of squares regression is really going to be calculated by taking the coefficient of determination and multiplying it by the sum of squares total. And the sum of squares total is actually sum of squares y, right? So 23.6 in this case times 0.75, which is the coefficient of determination. And then what's left involves the coefficient of non-determination, right? That's what 1 minus r squared is, again times sum of squares of y, 23.6. So between the two, the sum of squares regression and the sum of squares error, we've got all the variation accounted for. So then we need to look at the degrees of freedom for each of those. So for the first one, it's the k minus 1, which is the number of variables in the model. So there's 2 minus 1. And for the second, sum of squares error, the degrees of freedom is n minus 2, which is the sample size minus 2. So there's 10 couples. 10 minus 2 is 8. And that's what we've got there. And when we divide those things, right, you can see the mean square regression is just taking and dividing 17.7 by 1, so it's the same value. Anything divided by 1 is itself. The other one, however, 5.8 divided by 8 gives us 0.72. And then finally, the F statistic is calculated by dividing the MS regression, the mean square regression, by the mean square error. Okay, so that gives us a calculated F-score of 24.4. And then we need to use our F distribution to find out the critical value with these degrees of freedom of 1 and 8. Right? So 1 and 8 degrees of freedom is 7.57. Everything on this is a 0.025 one-sided, which is a 95% two-sided confidence interval, or corresponds to that. So we have a large F value, so we could actually be more confident in the findings, but essentially the model is significant since the F value exceeds the critical value of F, which means years of education is a significant predictor of the number of children. Now this last piece, this summary table, is just usually how the findings are presented. So again, we came up with our sum of squares regression and error. We're just going to include those in the table. And there's the total, which is the sum of squares of y, or the sum of squares total. That's the same thing. The degrees of freedom, 1 and 8. And then we add the degrees of freedom together for the total degrees of freedom, which is 9. The mean squares, which we calculated up here, and the resulting F value. That's usually how the ANOVA findings for a regression analysis are presented. All right, so that's it. Thank you.